Hello, I'm Pranav Madden, and today I'm going to talk about various causes of evolution. Now, evolution is simply when organisms change to adapt to their environment. Now, how do they do this, you ask? Well, the Hardy Weinberg principle states that the, the population, or there is an equilibrium which is disturbed by five things. The first of which is mutations. The second of which is gene flow, genetic drift, non-random mating, and natural selection. First off, let's talk about mutations. Now, mutations are simply changes in the DNA which fail to be corrected. Now, when nature gives mutations, nature doesn't decide whether they're good or bad. In fact, most mutations are probably random. So it really doesn't matter. And yes, there are mutations that don't do good in the environment. Like, for example, not being able to camouflage within your environment. Now, this can be bad if you're, let's say, a rabbit who accidentally got the albino gene. So, great. You're officially dinner for some random fox. Now, they can also be good mutations. Like, for example, will cause humans to be bipedal, which means we could run away from predators faster. Now, remember, when nature makes mutations, they are never random. All they do is, and if they're neutral, nature will keep them around just to keep genetic diversity in populations. Because if a population is too homogeneous, then there are going to be diseases due to interbreeding. This brings us to our next point, gene flow. Gene flow is basically when two different populations exchange genetic material. Kind of. So, in other words, let's just say that one group of people wants to go to another continent, and then they start life anew there, and then there's a fair amount of breeding between the two areas, and that could be an example of gene flow if you think about it, because it's simply the flow of alleles. And obviously this means that new alleles are going to be introduced into both populations, thus extending the genetic diversity of both populations. Now, what is genetic drift? It's a change in the frequency of alleles due to chance events, like, say, natural disasters, or overhunting, or poaching, or whatnot. Now, genetic drift, it actually happens quicker in smaller populations, and this is why it's better to have bigger populations, because genetic drift is not going to affect you as quickly if you're a member of a bigger population, and most of the alleles are relatively stable. But if you have a small population, some alleles will become extremely dominant, and others will just flat out go extinct. The bottleneck effect is when a population loses most of its genetic diversity and most of its members, so they're forced to have low genetic diversity even if they build their numbers back up. For example, the elephant seal. Even though their numbers recovered from endangerment, they have to be considered on the endangered list because they have virtually no genetic diversity. That said, you could put them in another area, give them let them evolve for a few thousand years and get them some new genes, and then take them back and cause them to reproduce with the old population, but that would take thousands of years. Now, another thing we have to discuss about concerning this is non-random mating. Now remember, mating is it's never random. It's always selected. For example, when birds tropical birds of paradise in, say, New Guinea select their mates, the female looks at the tail of a male, and if the bigger the tail, if it's more colorful, if it can sing better and dance better, then the female goes with the male that happens to be colorful and has a big tail. And pretty soon, the genes from the big-tailed male that's colorful, they have kids. Now to put this in human perspective, it would be kind of like where a woman has to choose between two guys. On one end, you have this guy that's extremely attractive, and he has all the good genes, and versus the guy with the bad genes. Now, most people would pick the ones with good genes. Now, going back to genetic drift, there's actually this thing called the founder's effect. An example of this would be when, say, the Amish people came over to America. Now, they didn't have that much, there weren't that much members, but they did regroup and have descendants. And as such, the populations weren't very large, but that could be considered a founder effect because it was a member of a population going into another area and then having descendants. Now, the downside of this is that there can be certain diseases. Now, onto our... sexual selection is when, say, they choose their mates based on if they look more beautiful. Let's just put it that. Now, finally, there's this thing called natural selection. Now, what is natural selection? It's a theory that organisms will adapt to their environment to survive, reproduce, and pass on their genes. An example of this would be if for some reason birds would eat rainbow butterflies. So I guess the butterflies that just so happen not to be rainbow butterflies, the ones that blend in with their environment, those live on, and those go on to mate and have kids. So therefore, the birds, when they're hunting out the rainbow butterfly populations can go down. You're only going to have dull-colored butterflies, to put it that way. In other words, if for some reason an organism has bad genes, then they won't be able to pass it on because if it isn't rejected by its own community, it's going to be starved. You're probably going to get disease, or probably going to be killed by another organism. Now, what is normal distribution? Normal distribution creates a bell curve where all the phenotypes have the same chance of surviving. Should natural selection occur, the curve will change. Directional selection is when an average that is greater than the actual average on a phenotype like that is favored. In other words, if the environment were to become cooler, then certain animals with thicker fur would become the average for their species. Another type of selection is stabilizing selection, where the average phenotype is selected against both extremes. For example, giraffe necks. They're really long because obviously they have to reach acacias. But originally their necks were very short, but they couldn't reach the acacias. And then there was this long-necked giraffe, and it reached the acacias, and their genes were passed on until you reach modern giraffes. The final type of selection is disruptive selection, where the selection is against the average, and extreme phenotypes on both sides are selected because they have an advantage in the environment. Thank you very much for listening to my presentation about natural selection and the cause of evolution. Have a great day.